arc length and the TNB frame. Let's take a parametrized curve in 3-space, x equals x of t, y equals y of t, z equals z of t, for t between a and b. And we'll assume that the component functions have continuous derivatives, namely dx dt, dy dt, and dz dt are continuous. The arc length of this parametrized curve is given by L equals the integral from a to b of the square root of the sum of the squares of the derivatives of the component functions dt. So the square root of dx dt squared plus dy dt squared plus dz dt squared, all as the integrand inside the integral from a to b dt. Just note that if we were doing this in 2-space, it would be analogous. So in 2-space, we would have the integral from a to b of the square root of dx dt squared plus dy dt squared dt. Both of these formulas are exactly the same when you express them in terms of the length of the derivative, right? The square root of dx dt squared plus dy dt squared plus dz dt squared is just the length of dr dt. And same goes if we're in 2-space. So a single arc length formula that works independent of the dimension is that the length is the integral from a to b of the length of dr dt dt. Let's try an example. Compute the arc length of this parametrized curve. As always, you should pause the video and try this example yourself first. Okay, so we have x equals cosine t, y equals sine t, z equals t, t between 0 and pi. So using the arc length formula, the length is the integral from 0 to pi of a square root of a sum of the derivatives squared. Well, the derivative of cosine t is negative sine t, the derivative of sine t is cosine t, and the derivative of t is 1. So we just plug those derivatives into the arc length formula. Now, the square of negative sine t plus the square of cosine t, that's just sine squared t plus cosine squared t, which is 1. Adding another 1 for 1 squared, we get 2. So we just have a square root of 2 as the integrand. When we integrate that, it's just the constant root 2 times t from 0 to pi. Plug in the pi, we get root 2 pi. When we plug in the 0, we just get 0. So the final answer is just root 2 times pi. Arc length parametrization. It's important to understand that there are infinitely many ways to parametrize any given curve. One particularly nice way to parametrize a curve is using an arc length parametrization. The idea is that we start at a specific reference point, and whenever you plug in a specific value for your parameter, you get a point on the curve that's exactly that many units away from the starting point along the curve in terms of its arc length. So the arc length parametrization formula is the following. S is the integral from t0 to t, the length of dr du du. The idea here is that we're changing an arbitrary parameter t into an arc length parameter s. Notice that the formula is exactly the same formula as for computing arc length, except the upper limit is a variable. It's the variable t. Also, we changed the name of the dummy variable from t to u because t is already being used as the upper limit. But the dummy variable u doesn't actually appear in the computation, so it doesn't matter whether we called that t or u. Okay, let's try an example. Change this arbitrary parametrization of this helix to an arc length parametrization, where the starting point, r of 0, is the point 2, 0, 1. Once again, pause the video and try to do this yourself, and then resume the video to check your answer against mine. I just want to mention that the reference point here is the point 2, 0, 1. That's the point that corresponds to the t value of 0. Notice that if we plug a 0 in for t into the original vector valued function, we get 2 times cosine of 0, which is 2 for the I component, 2 times sine of 0, which is 0 for the j component, and the k component has a constant of 1. Okay, let's go through the steps. First, I'm just going to change the t to a u. So r of u is 2 cosine ui plus 2 sine uj plus k. I just changed the name of the variable. Now we take the derivative. dr du, or equivalently r prime of u, is negative 2 sine ui plus 2 cosine uj. The k component goes away. Now let's take the length. So that's the square root of 4 sine squared u plus 4 cosine squared u. We could factor out the 4, and we have there sine squared u plus cosine squared u, which we'll use our main Pythagorean identity to change to a 1, and 4 times 1 is 4. And finally, the square root of 4 is 2. So that's going to be our integrand. So s is the integral from 0, right? That's the t value corresponding to the reference point, up to t of the length of dr du. And we just found the length of dr du, or the length of r prime of u, to be 2. So we get 2u from 0 to t, which is just 2t. So we now have a relationship between the parameter that was given to us and an arc length parameter with the given reference point. Solving for t, we have t is equal to s over 2. We can now replace t by s over 2 in the original parametrization to get our arc length parametrization. R of s is equal to 2 cosine s over 2i plus 2 sine s over 2j plus k. Let's try another example. Let's take an arbitrary line parameterized by r of t equals r0 plus tv. Notice that r0 is a given point on the line and v is a vector parallel to the line. Once again, pause the video and try to change this parametrization to an arc length parametrization. Okay, so once again, I'm just going to change the t to a u. R of u is r0 plus uv. Take the derivative, and we get just v. R0 is a constant, so it goes away. And then we have a constant vector, v times u, which just gives us the constant vector. Now, s is the integral from, again, 0 to t of the length of dr du. The length of dr du is just the length of v. The length of v is a constant, so we just get the length of v times u from 0 to t, which is t times the length of v. It follows that we can express t in terms of s as t equals s over the length of v. So we replace t by s over the length of v in our original parametrization to get our arc length parametrization. R of s equals r0 plus s times v over the length of v. What we've just discovered is that we could change an arbitrary parametrization of a line to an arc length parametrization simply by normalizing the vector that we used in the definition of the parametrization. So as long as you're using a unit vector for the vector that's parallel to the given line, you will automatically have an arc length parametrization. Let's do a specific example. X equals 2t plus 1, y equals 3t minus 2, with reference point 1, negative 2. Note that I chose the reference point corresponding to t equals 0. So pause the video and see if you can write an arc length parametrization for this line using the formula we just derived. Then resume the video to check your answer with mine. Okay, so the given vector is the vector 2, 3. We want to normalize that. The length of this vector is the square root of 4 plus 9, or the square root of 13. So we're just going to replace the 2 by 2 over square root 13, and we're going to replace the 3 by 3 over square root 13. And we have our arc length parametrization. And notice I just used the variable s to stress the fact that this is actually an arc length parametrization rather than an arbitrary parametrization. Notice that ds dt is just the length of dr dt. This follows immediately from the fundamental theorem of calculus. Also, the length of dr ds is 1. Let's see why that's true. By the chain rule, dr dt is equal to dr ds times ds dt. So solving for dr/ds, we have dr/ds is dr dt over ds dt. But we just saw that ds dt is the length of dr dt. It then follows that the length of dr/ds is the length of dr dt over the length of dr dt, which is 1 over the length of dr dt times the length of dr dt, pulling out the constant in absolute values in front. And that is just equal to 1. One more property. So if you have an arbitrary parameter t, and for all t the length of dr dt is 1, then t is an arc length parameter. So let's see why. Suppose for all t the length of dr dt is 1, then s is, as always, the integral from t0 to t length of dr du. And we could just replace the length of dr du by 1 because that's what's given. And that's just equal to t. So when we try to get the arc length parametrization, it's already equal to t, showing that t is already an arc length parameter. From now on, we want to mostly work with curves that are called smooth. A curve C is smooth on an interval if C can be parametrized with a vector-valued function r of t, whose derivative is continuous and non-zero on the interval. Essentially, a smooth curve has no sharp edges or cusps. When the tangent vector to a smooth curve turns, it does so continuously. For the rest of this lesson, we will be assuming that any vector-valued function r of t is smooth. Now we're going to talk about the unit tangent, normal, and binormal vectors. The unit tangent vector, t of t, is defined by taking r prime of t and dividing by its length. In other words, we just take the tangent vector we get by differentiating the vector-valued function and normalize it. Since the length of t is 1, it's constant, t of t is orthogonal to its derivative. Let's prove that. T of t dot t of t is the length of t squared, which we know that the length of t is 1, so this is equal to 1 squared. It actually doesn't matter here that that number is 1. It could be any constant, and this argument will go through. Okay, so 1 squared is 1. Differentiating each side of this equation, the derivative of 1 is just 0, so that's equal to the derivative of t dot t. By the product rule for the dot product, we have t dot t prime of t plus t prime of t dot t of t, which, since the dot product is commutative, is equal to 2t dot t prime of t. Dividing by the 2, we see that 0 is t dot t prime of t, showing that t and t prime of t are orthogonal as we wanted. Okay, so it follows that t prime of t is normal to the curve C at t. And of course, as long as t prime of t is non-zero. We define the unit normal vector n of t by normalizing the derivative of the unit tangent vector. So n of t is t prime of t over the length of t prime of t. Finally, we define the binormal vector to be the cross product of t and n of t. Note that the length of b of t is the length of the cross product of t and n of t, which from our theorem on lengths of cross products from the cross product lesson is the product length of t times length of n of t times the sine of pi over 2. The pi over 2 comes from the fact that t and n of t are orthogonal. Therefore, they form a 90-degree angle or an angle of pi over 2. Each of these factors is equal to 1 because t and n of t are unit vectors. This shows that b of t is also a unit vector. Here's a picture of an arbitrary curve illustrating what t, n, and b might look like at a point t0. Notice that all three of these vectors are mutually orthogonal to each other. This is known as the TNB frame. I just want to mention a couple other formulas that you could use for computing some of these things. I'm not going to go through the proofs of these because they go a little outside of the scope of what I want to do here. So first, B of t can be computed directly by taking the cross product r prime and r double prime of t and dividing by the length of that. I won't use that formula in this lesson, but sometimes this formula can save you a lot of tedious computations rather than computing n first. Sometimes computing b first is the way to go. If you do compute b first before n, then you might want to also use the formula n of t is b of t cross t of t. Let's try an example. See if you can compute the unit tangent, normal, and binormal vectors for this parametrized curve. As always, pause the video, try this yourself, and then resume the video to check your answer against mine. So we have x equals a cosine t, y equals a sine t, z equals ct, where a is greater than 0. Okay, notice that a and c are both constants, and we're insisting that a is positive. Just for your reference, I'm going to put up the formulas I'm going to use for t, n, and b. Let's start by rewriting the parametrization as a vector-valued function. R of t is a cosine ti plus a sine tj plus ctk. R prime of t is negative a sine ti plus a cosine tj plus ck. The length of R prime of t is then the square root of the square of negative a sine t plus the square of a cosine t plus c squared, which under the square root, we have a squared sine squared t plus a squared cosine squared t plus c squared. We could factor out the a squared and use our main Pythagorean identity to replace sine squared t plus cosine squared t by 1. So this simplifies to the square root of a squared plus c squared. Okay, so we have the length of r prime of t is the square root of a squared plus c squared. We can now compute t of t by dividing each component of r prime of t by the square root of a squared plus c squared. So we have t of t is negative a sine t over the square root of a squared plus c squared times I, plus a cosine t over the square root of a squared plus c squared times j, plus c over the square root of a squared plus c squared times k. Now to compute n of t, we're first going to have to compute t prime of t. T of t looks a lot more complicated than it is because most of those expressions are constant. So we just need to differentiate sine t for the I component to get cosine t, and cosine t for the j component to get negative sine t. The k component goes away because c over the square root of a squared plus c squared is just a constant. The length of t prime of t is simply a over the square root of a squared plus c squared. Dividing by that, we get n of t to get negative cosine ti minus sine tj. Finally, we get b of t by taking the cross product of t and n. Notice in this determinant, I put the components of t of t in the second row and the components of n of t in the third row. And you can check that when you do this computation, you get c sine t over the square root of a squared plus c squared I minus c cosine t over the square root of a squared plus c squared j plus a over the square root of a squared plus c squared k. I briefly mentioned the TNB-Frame earlier. The TNB-Frame looks like this. Given a curve C defined by vector-valued function r of t, at any given point t0, we can compute t of t0, n of t0, and b of t0. What we get is a little three-dimensional coordinate system because t, n, and b are all mutually orthogonal. So we see that in those three green vectors there. What happens when we look at t, n, and b, we get something that looks like three-dimensional space. And in particular, we get the analogs of three coordinate planes. The tn plane is known as the osculating plane. The TB plane is known as the rectifying plane, and the NB plane is known as the normal plane. It's not too hard to write down equations for these planes because generally speaking, you'll know what the point is. It's the point corresponding to the parameter value t0, and the vector, which is normal to that plane, is just one of these three vectors, the one that is not making up the plane. So for example, for the osculating plane, a normal vector to the osculating plane is b of t0. A normal vector to the rectifying plane is n of t0, and a normal vector to the normal plane is t of t0. Let's try an example. As a hint, for this example, you could use t, n, and b that we found in the previous example and just substitute in the appropriate values for a and c. Go ahead and pause the video, try this example yourself, and then resume the video to check your answers with mine. Find equations of the osculating, rectifying, and normal planes to the following curve at the point 0, 1 pi over 2. And the curve is x equals cosine t, y equals sine t, z equals t. You may recognize this from a previous lesson as a circular helix. And notice that the t value we're concerned with is t equals pi over 2. The easiest way to see that is just to look at the third component, because that's z equals t. That directly tells us that t equals pi over 2. And then notice that the cosine of pi over 2 is 0 and the sine of pi over 2 is 1. So that t value matches up nicely with that point. Just for our reference, I'll put a little copy of the picture of the TNB-Frame up so we know which vectors we're looking for which planes. From the previous example, we found t of t, n of t, and b of t for this general curve, x equals a cosine t, y equals a sine t, z equals ct, where a is positive. Letting a and c both be 1 and t equal pi over 2, we see that t of pi over 2 is negative 1 over root 2i plus 1 over root 2k. N of pi over 2 is just negative j. And b of pi over 2 is 1 over root 2i plus 1 over root 2k. We can now use those three vectors together with the point 0, 1 pi over 2 to write equations of the three planes. For the osculating plane, we're going to use the vector b to get 1 over root 2 times x minus 0 plus 0 times y minus 1 plus 1 over root 2 times z minus pi over 2 equals 0. And that simplifies to 1 over root 2x plus 1 over root 2 z minus pi over 2 equals 0. For the rectifying plane, we're going to use the vector n. So since there's only a j component there, we get negative y minus 1 equal to 0. And finally, for the normal plane, we're going to use the vector t. And we get negative 1 over root 2 times x minus 0, or just x, plus 1 over root 2 times z minus pi over 2 is equal to 0.